the same places. Okay, so you might get an initiation of the cancer with the virus, but then you'll get progression with the chemicals because they will cause extra mutations. Usually it's a progression of mutations that will lead to cancer, as well as the initiation. So these are some of the steps in molecular carcinogenesis. Don't worry about this table. I've got lots more coming up. But you can see that there's a activation, and often the virus will cause the activation. And a chemical change will happen. This will make the cell more likely to grow out of control. And then there'll be a tumor formation, and then the tumor will get malignant and spread, and then you have clinical cancer. So these are some of the steps involved. There's many places in the cell where you can trigger cancer, in the mitochondria, in the receptors, in the DNA, in the communication pathways, and many ways to alter the cycle and the normal life and death of the cell. That's what cancer does. It stops the normal life and death and the normal programmed death, and it makes it live forever. So basically, it keeps dividing and living way beyond what it should. So the cell cycle is this. There's the stages of mitosis. You can see where the cell prepares for division. It lines up all the DNA and chromosomes on the center plate. Then they double them first, and then they separate. And so there's two copies go to each cell, and it divides. It goes around that whole circle. Well, there's a couple of restriction points along the way. Normally, proto-oncogenes, these are things we have in our body that normally say, okay, let's start dividing. And oncogene means cancer. But their normal function is not cancer, it's to start the cell division. Now the virus will take over that proto-oncogene and becomes a viral oncogene. And that makes the cycle go when you don't want it to go. And then it gets to a restriction point, the RB restriction point. That's a retinoblastoma restriction point. That's a gene that says, well, I'm not sure that we're ready to complete division because you don't have enough product. You don't have enough proteins or whatever. And the virus will say, oh yeah, we're going to get past here. And what it'll do is it'll affect that restriction point. And here you can see what happens is at the bottom there's an RB. That RB is the restriction point. It'll phosphorylate and put 3 phosphoruses on it. When it does that, it suddenly goes into cell division and it says, okay, let's finish mitosis. So the virus can get past it by phosphorylating that retinoblastoma gene and get the cell cycle going. Transformation of a cell doesn't produce virus particles, and it doesn't kill the cell. It prevents it from dying. But normally a cell has to die. It's its normal job. It becomes immortal in cancer. And so the viruses that get into these cancer cycles, they're actually preventing the cell from normal death. And there's a gene called the P53 gene that says, whoa, you're not obeying the rules of this here cell division in this area, in this tissue. I'm going to kill you. And the P53 gene will say, you're dead, boom. Shoot him, you know, and he's out of the picture. But then the virus will come along and say, okay, P53 gene, I'm going to deactivate you. And the virus will deactivate the P53 gene, and all of a sudden the normal cell cycle is no longer being controlled by the cell. So there's another way to kick this whole system, the cycle on, is the viral T antigens will bind to that retinoblastoma gene, and this will also cause it to go into mitosis cycle, cell division. But there's one more hurdle it has to pass to complete the cell division and reproduction, replication. It has to get past the P53 gene, which is a little policeman. Okay, and the P53 gene has many jobs and it's hugely powerful in our system. And the viruses have figured out a way to deactivate it, and they will do that. HPV has antigens that actually they call them tumor suppressors. No, we'll get to it. I'll show them to you. I'll show you a picture of it. So this is what the virus will do. It deactivates the P53 gene and causes eternal division of the cell. Okay. This is the tumor suppressor gene, P53. It's on chromosome 17. It can stop and check a damaged DNA strand and repair it. So it'll actually fix the thing. If it can't fix it, it will kill the cell. So it's a guardian of the genome. And if the damage on the DNA is irreversible, the P53 gene will kill the cell, and that's its normal job. These are all of the factors that influence the P53 gene. Mitosis, catastrophes, telomere erosion, DNA strand breaks, ultraviolet radiation, blah, blah, blah. Reactive oxygen stress, ROS is really important. And on and on. Anyway, its normal job is homeostasis and survival and inducing death. So you can see how important it is. And we need to protect the P53 gene. These are some of the action of cancer-causing viruses. I've got the chart on the back of that sheet over there if you ever want to look at it. But it shows you these viruses in the brown boxes affect the normal cell cycle in many ways. And they act as tumor suppressor. They deactivate tumor suppressor genes. They deactivate Mr. P53, and they interfere with signals, cell signals. So oncogenes are normal cellular genes that regulate cell growth. I told you that already. I call them C-onc. After a virus transforms them, mutates them, they become V-oncs, and V-circs, V-mic, V-ras. So these guys will lead to activated oncogenes will lead to cancer cells. And now the epigenetic component is the part that is interacting with the environment. There's cues in the environment, chemicals you breathe, chemicals you swallow, and pheromones in the air, phthalates, plastic, whatever. They have these effects, and viruses will do this as well. So what they do is epigenetically inactivate your tumor suppressor genes, and there's a lot of them, and they will de-repress oncogenes or cancer-promoting genes, which means that they'll turn them on. So these are nasty. Ras proto-oncogene is one example. I'm not going to waste a lot of time on those. Here you can see the P53 is a target for the oncogene proteins of SV40 virus, adenoviruses, human papillomaviruses, and measles viruses. So I've just added that in. But you can also see that a lot of these tumor suppressor genes are very specific to the type of cancer that they are associated with. So there is a specificity, and it gives the doctors a chance to target particular therapeutic tumor suppressor genes. Okay, so this is a sort of a sequence of mutations that lead to colorectal cancer. It's not just a one-step process. There's chromosome instability. There's microsatellite instability. CpG island methylation. That's the epigenetic effect. Yeah, don't worry about notes. I'll give you a disc after. The chromosome instability. And a chromosome becomes unstable, it can lead to cancer. KRAS, the RAS gene does that. You can inactivate at least 3 tumor suppressor genes, APC, P53, and loss of heterozygosity in the long arm of chromosome 18. There's mutations of TGFBR and P3 CA genes, recently described. So you can see a cancer is not just one shot, one chemical, one thing, one cancer. It's a progression of mutations that also follow. There's two pathways to colorectal cancer. You can see there's a lot of mutations there. But P53 is the one that goes right at the very end when it becomes really bad. This is chromosome instability and microsatellite instability. Now, microbiota are the stuff, the bug in your tummy. They can release interleukin-17, which is a pro-inflammatory cytokine that causes damage to a STAT3 gene, which regulates growth, cell growth and division, and cell movement. And self-destruction of cells, apoptosis, which is normal death. So the interleukin-17 is produced by these bacteria in your intestine. So they do have a potential to contribute to carcinogenesis. This is the breast cancer carcinogenesis, normal route. Don't bother memorizing that stuff, but you can see that there's an initiation, pre-initiated cell, initiated benign tumor, and then cancer. So it goes through a whole progression. This is biocarcinogen exposure. This is benzene leukemia. It creates some really nasty chemical compounds, intermediates that mutate things, produce tremendous amount of reactive oxygen, which can damage your DNA. It's really bad for DNA. This is chemical carcinogenesis showing that